Yeah.
Okay, so welcome everyone to our weekly seminar at the Institute of Astrophysics. Today we have the pleasure to have with us Alejandro Mus, who is actually here for a week to collaborate with us, to work with the SMILE group. So you find him at the guest office 2016. So for any question, he will be here till Friday. You can pass by his office. So briefly about Alejandro. So Alejandro completed the PhD at the University of Valencia, focusing on very long baseline interferometric imaging algorithm and calibration techniques. His research resulted in several publications covering topics such as transient searches in the galactic center, polarimetric techniques, and algorithm for constructing movies from observation. He was awarded the Outstanding PhD Award by the Event Horizon Telescope Collaboration for advancement in image reconstruction in radio interferometry for objective and multidisciplinary approaches. Currently, he's a postdoctoral researcher in Cagliari, Sardinia, where he is developing the first archive of ALMA Aegean sources observed in global campaign, which means where ALMA was observing in VLBI mode together with, for example, the GMBA or EHT array. So for those who are interested in ALMA data, for example, the archive processes the continue. Let's see. The archive processes and present ALMA data products ready for scientific use. So additionally, he's also working on scattering mitigation techniques in the galactic center, aiming to improve the clarity and the resolution of astronomical observation in this region. Sorry, 1 second. There is some zoom. What is still recording? Okay, we're fine. Alejandro, the floor is yours.
Okay, thank you. Thank you very much, Carolina. I want to thank Carolina as my group for giving me the pleasure and the opportunity to work with them here this week in this very beautiful island, as is Crete. Thank you all of you for coming to my presentation. And before starting, I have to admit that at the beginning I was thinking, okay, since I'm coming to work on these imaging techniques for the SMILE project, I want to focus my talk in imaging algorithm. But how can I do for present this in a broader way? Because maybe there are some people in the audience who is not very familiar or expert in VLBI. So I was trying to balance, to try to find the sweet spot. And suddenly this Mitigation paper appeared. I don't know if you even saw it, the image of say this is star reprocessed by another collaborators of Japan, and they were claiming some, under my point of view, but I'm not gonna give my opinion. I just refer to the answer of the EHT to that. They were getting some different images of Sagittarius star than the ones presented by the EHT. So I said, perfect. Let's do this talk in a way that people at the end of the talk, people who is not expert VLBI, can understand, for example, why there are some different images in Sagittarius star. What are the difficulties that may arise during the imaging process? And when they see an image of VLBI, to have this way of thinking of, is this image correct? Is this image, how was it done? Who did it? And why they may appear several images from the same source, even if the whole process is the same, even if the same person is doing So I hope at the end of this talk, yeah, true. At the end of this talk, I can give you an answer to all of this, and you can answer it the next time you see an image from VLBI. So my talk, I divided in these subsections. So first, I want to very briefly introduce the VLBI technique, very long baseline interferometry. I will give some actual, right now, imaging methods and some warnings that we have to have in account. And then I will present my work about some new algorithms that we have been developing to overcome most of the limitations, or very big limitations, that previous algorithms for imaging, for VLBI imaging had. I will show some results of these algorithms in the static and dynamic domains, so recovering images and movies of sources, and also very recently submitted paper reconstructing the scattering screen in the galactic center from observations. Let's start with a taste on very long baseline interferometer of VLBI. So for those of you, I guess all of you know a little bit the idea of VLBI, but we astronomers have the problem of the diffraction. We can have a big telescope, and will be limited by its size, right? We can go a step further and build interferometers and combine different antennas to build or to emulate a bigger telescope that wouldn't be feasible to build because it cost or physical conditions. Like ALMA. For example, this is a super instrument. I'm really fall in love with ALMA, but then we can go one step further and say, and why do we have to restrict ourselves in a few kilometers? And why don't we cross, for example, continents? And we combine telescopes in the different parts of the world to emulate an Earth-sized telescope. So we observe with antennas at different places of the world, and we correlate the visibilities right now in two parts, in high stack and in bond. For example of this is the GMBA, the EST, the KBN, the Korean Very Long Baseline Network, the EBN, etc. So just an animation, for example, for the EST, 2017, and this is important. I want just to show 2017 because I will talk about the result 2017. We combine telescopes, 7 telescopes, and yeah, this was our interferometric instrument. And with this technique, we can observe these beautiful images. For example, the persistent ring across years 2017 and 2018 of M87. M87, it was in a particular strange state in 2017. I'm not going to do spoilers, but follow the results of the EST now when we submit the polarization and 2021 observing campaigns. We can also observe this. I really like this image. This was submitted and published a few months ago by one of the algorithms that I will talk today about and resolve. At 86 gigahertz, we can see M87, we can see the whole of M87 and the jets in the northern and the southern part. That resolution was never achieved before. This is with the GMBA at 86 gigahertz. We can see we were able to see there is a star at 230 gigahertz. And these different cluster solutions. And this is one of the points, that's why I was showing it here, that I will talk about the problem of the non-unicity in VLBI observation, the non-unicity of the images recovered. And also, we can have, for example, we can see these beautiful images of Centaurus A using different instruments at different frequencies. So VLBI technique is a very nice technique, but is poorly constrained. What does it mean? So we have a hard ill-pose inverse problem. Why? Our image is not than the model image that we may don't know multiplied by the dirty beam plus some hopefully Gaussian noise, but not always not Gaussian. This is related by the technique theorem in Fourier transform with the visibility. So we actually observe visibilities, which are the convolution of some model with the PCF plus noise. The problem with VLBI is that this PCF, the point strength function, is very sparse. Meaning that there are many visibilities, models, or many images that fit the data. So for one observation, one VLBI observations, we don't have one image. We have infinite images that satisfy the constraint and satisfy this equation. And this is why we have to be very careful when doing imaging with in VLBI. So for example, I did this animation. This panel give us is the real source. This is the simulated aperture. This is the reconstruction, and this is the telescope. As we include more and more telescopes and we let the Earth rotate, we are constraining more and more the image. Of course, when this PCF is fully complete, the problem is not ill-posed anymore, because there is only one image or one model in the visibility that satisfies the question. But when it's poorly constrained, we have many of images, candidate images that can be solution of our problem. Sorry, what is in particular, one really important key of VLBI is that every visibility matters. Every visibility is gold. So if we have, for example, this reconstruction that I did of M87, we start with 223 observations. Just, you see, 223 observations is nothing to construct M87. And when we start to flag some of them, we just lose all the images. So imaging in VLBI is very complicated. Even if we get an image, we may know. Yes?
How do you know the real image?
This is a very good question. We don't know the real image. So we have to live with this uncertainty. And this is something that I'm usually missing when I see a paper VLBI with very sparse array, and they show one image. This is one of the many images that they are. The more constrained the array, the more telescope you have, the less difference there are between images. But I will show later some of cluster of many solutions that fit the data, that are mathematically solution of the imaging problem, and they are really bad. We wouldn't consider as publishable images. So VLBI imaging methods. Let's go to that. We can classify in two main families: backward imaging method and forward imaging method. Backward imaging methods, you start from the image, you go to the visibility plane and you operate it. And it's called backward because you do the inverse transform. While forward, you suppose you have some binary distribution, some image, and you go to the visibility domain and you operate it. And it's called forward because you do that dialog for image. In the backward domain, clean. Most of you know clean and all its variants. In the forward, which is the one we like more in VLBI for many reasons, and we can discuss later why I think clean should be very carefully taken in VLBI. We have optimization methods. For example, RML is the most known maximum regularizing method. It was used also in M87 and C2C*HT, Bayesian methods, and machine learning. So optimization methods, they are deterministic, they can be quite expensive, and they are well tested. However, when the array is very sparse, the UV coverage is very sparse, they have hard time to interpolate the gaps between the visibilities, to guess, to proper find these missing data points that are missed because there are no visibilities, there are no telescopes observing to fill these gaps in the UV coverage. Bayesian instead, I will say they can kill flies with cannon, as we say in Spain, meaning they explore everything. They just start from the visibilities and they explore this comrade from the fringe fitting. You can start the fringe fitting with comrade and get Full-Stokes polarized images. So they explore all possibilities and the gains on the calibration, on the bandpass, on everything. But of course, this takes a lot of time, a lot of resources. And machine learning. Machine learning, for me, machine learning is a little bit controversial because you don't know what is happening under the hood. And in a very, very sparse, very ill-posed problem, you don't know how it's interpolating these missing data, these gaps. So as I said, imaging problem in VLBI has potentially infinite solutions. What is a good image? What is a bad image? It's based on the astronomer's expertise. It's based on some subjective ideas, based on some metrics. Are the metrics good? Are the metrics bad? We are having this philosophical question right now in DHT, trying to find the movies CTRC star. Are the metrics we are using good enough? What will be a good metric? So this is the Miyoshi image of Sagittarius C star. Of course, it's absolutely different, and this is composed, absolutely different to the ring we were seeing in DHT. They were doing some mistakes. Some mistakes. I don't think Miyoshi did it without knowing. He's a very, very good astronomer. But of course, when you clean, because he was using clean, we were using several methods, and I will explain later some short story, very fast story that we had in DHT. You can fill the gaps of your sparse array as you want. So Miyoshi was placing this cleaning mask in some points where there not may be data. And of course, it cleans, and find something. And then you can say, okay, this is the image of the Sagittarius star. And the good thing for them is that this image fits the data. What does it mean that fits the data? For example, the chi-square, the difference between the model and the observed data was close to 1. Why? Because since the array is very, very sparse, and the source is very complex with the scattering, with the variability, there are many, many, many solutions that can fit the data, even this potato here. But it's nothing that we didn't claim before, because here when I show these clusters, what we did in this is we obtained 12 million of images of Sagittarius C star using different methods. Among these 12 million images, the most probable one, the most repeated one, was this one. The second most repeated, this one. The third, and the fourth. And of course, the fourth was not dreamlike. So, depend on the algorithm you use, depend on the parameters of this algorithm, you may end up in non-ring structure that still fits the data. So that can be solution of your imaging problem. And that's why in VLBI, we have to be very careful when we do imaging, because we can find potatoes that fit the data, even if your potato is not what you are actually seeing. So are the metrics good? What is a good metric? We have to be very, very, very good. And for this, I struggle to be convinced in machine learning applied to VLBI, because we don't know what it's doing under the hood, and anything you can do, you can obtain some potato that fits your data. So till now, what do we have? Clean base. Many high experienced people doing clean. Traditional RML optimization needs to explore some hyperparameters. That's why the reason we were doing 12 million images. Bayesian, maybe too expensive. Maybe we have to wait, or we had to wait 1 month for obtaining one image, say there is this star, using some of this Bayesian algorithm. It may not be feasible. Machine learning, hard to justify. maybe because I'm not expert in machine learning, and some people, for sure, people here are more expert than me. But under my point of view, this is hard to justify. So what do we do? So I am a mathematician I studied mathematics, and when I saw these problems that generally are not convex, if you focus in this RML, and we get one solution of this non-convex problem, and we say this is the image. No, this is one of your infinite images, one local minimum among your infinite local minima. This was a little bit, I was not very comfortable. Also, this exploration of 12 million images, we cannot do it in a normal computer. We have to build some clusters in Google Cloud, etc., etc. So how can we do this more accessible to everyone and still be rigorous mathematically with the problem? So we introduced multi-objective optimization, which is a version 2 of traditional RML. This lives in the world between Bayesian exploration and optimization method, but getting the best part of the two worlds. So it's faster than Bayesian and still more rigorous than RML. And the good point is that we can recover the set of all possible images. I want 12 million images that fit the data I can recover. And I will explain with some examples then. Now, I just only have this equation and one more. Sorry for that. Traditional RML methods. What is doing? I want to minimize this functional here. The solution of this functional is an image, it's a movie, depending on what I have. These S are data terms, are metrics. So for example, the chi-square with respect to the visibilities, with respect to the amplitudes, with respect to the closure phases, closure amplitudes. And the R's are what we call regularizers and impose some condition on the image. For example, I want to promote sparsity. I want the image to be the most constant possible. I want to be smooth, etc. I want to include some dynamic imaging. I want to recover a movie, will be another regularizer. Problem, this alpha, beta, gamma, blah, blah, are not known a priori and must be explored. What does it mean? What we did, for alpha in range, blah, blah, for beta in range, blah, blah, for gamma in range, blah, blah, 7 nested force, and we explore find set of alpha, beta, gamma. For every of this combination, we got one solution of this non-convex problem. So you can imagine how many solutions we were missing. For every combination, we were missing infinite solutions. So needs to be improved, at least on the mathematical point of view. And we said, okay, let's introduce the multi-objective optimization. What we want to minimize is not this, but a set of 7 functions that can be contradicting each other. For example, let's try that we want to find a path between here and the Knossos Do we take the cheapest route, the fastest route? There are actually many. I can take cheapest, the fastest. I can go and do a greater route. I can put Google Maps, and Google Maps is offering me some of these solutions. But all the ways lead to Rome. Right? I have many solutions, but all of them are solution of our problem of finding the way from here to Knossos. The set of this solution is what we call Pareto front, and it's here. The Pareto front are all the images, movies, whatever we are doing solutions that best balance between these regularizers. The best balance, the data term, the metrics with respect to the smoothness that we want, with respect to the sparsity that we want. So we can have all of the ways and all the dependency between all the ways. So multi-objective optimization seems to be the correct mathematical way to go, or one of the probably correct. And what we did? So we formulated two cases, two ways to study the dependence of every regularizer with respect to all the data terms, or just how the regularizers affects the final data terms. Those are two different philosophies. Both give the set of all possible solutions, but seen with two different perspectives. For example, the first one, what we call MoID, we call now this is a non-optimization method, which stands from multi-objective optimization evolutionary algorithm by decomposition, explore the relations among all the data terms and give the best compromise. So explore all the ways from here to Knossos and give the one which is not the fastest, not the cheapest, but the one that best compromises the fast and the cheap. But also gives you the faster, the cheapest, and the slowest. Give you everything. Instead, this PCO, which comes from particle swarm optimization, find the best alpha, beta, gamma, blah, 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 associated to the image. Both are complementary, means that they have the cons and the pros. For example, when I did returns many local minima the user wanted, I want 1,000 of movies, I get 1,000 movies. I want million of images, I get million of images. But of course, it's slower than a simple optimization problem, because genetic algorithms can be slow. Instead, PCO gets only one image, but seeks the best weight combination. So what it's doing is, I don't really care much about all the possible ways, but I only care to arrive from here to Knossos, but I only care the one that give me the best value among velocity, chip, and speed. Both are very flexible, reduce the computational cost of traditional RMLs, and give interesting byproducts. For example, we know, in this example here, we know how data behave with respect to this regularizer. For example, I will say, if we want to have good metrics, good data terms, I can promote too much the sparsity. The sparsity. I rather prefer not very sparse image and a smooth image. This here is what I said is the Pareto front. PCO is finding the closer one to the ideal, while MoID is giving all of these possible solutions. Some nice byproducts. As I said, we have all the dependency between data terms and regularizers, and PCO gives the marginal contribution. What does it mean? This is a real image, Emily 7, April 11, sorry, done with PCO. We did, as I said, for this case, it was less. It was 7 million images, if I remember well. 7 million images, exploring a lot of combinations of alpha, beta, gamma, delta, blah, blah, parameters. Well, PCO is telling you, L1 is very constrained. It has to be on this range. Whatever is outside of the range will give you a very, very bad image. Instead, TV accepts more range of values, so you don't need to explore it, because any of these values here will give you a good image. So all of these 8 million parameters that we did can be summarized in this data. All that was falling out of this box plus here was not a movie, was not an image selected by the EST. Some examples, and this is where we start to see and answer the question you were doing. For example, let's try to recover the crescent using MoID. We have, this is simulating April 10 Emily 7 UV coverage. We were doing 3,000, we were asking for 3,000 solutions. And we clusterize by similarity, meaning solutions that differ 15% are considered in the same cluster. Differ up to 15% are considered in the same cluster. cluster. Then the others are other clusters. Here we see then a summary of 3,000 solutions. That still fit the data, even the dirty image, even this very bad image could be a candidate, is a mathematical solution of our problem. Even this image, we don't like it. We have to live with this, but those are mathematical solutions. Those are the potatoes Miyoshi could recover and fit the data. We don't like it, but still are solution of our problem. We develop some ways to select clusters, which are the most probable solution and the one with better weight combination. This is also real data. We see, for example, in the real data, very bad solutions. Those are solutions that Miyoshi, for example, or anyone could get and say, an independent analysis, I got this. No, it's not an independent analysis. It's another solution of the same problem. Movies. So we are working now in recovering movies, and a paper that is in process, in preparation, with one student of the group in Granada. And what we were doing is, let's take a data set, simulating what we call in this the best time windows in April 7. So 3 hours, scans of 4 seconds, and we wanted to 7 antennas, 6 antennas because at the half of the observation one was flagged. And we want to recover this movie. This is the true movie, simulated true movie that we are doing. And this is the recover polarization movie that we are getting with our solutions, with our method of PCO in this case. We see, for example, here how the hotspot, they are not synchronized, I think, but whatever. We see here how the hotspot is moving around and appears and then moves here, and how the polarization is consistent. Or what if we have some scatter ring and a hotspot that is crossing like this? So we here in this movie, we are recovering the hotspot movement. Maybe it's not a very, very clear movie that we would like to, but I recall here we have 6 antennas, 6 antennas. So this is in the edge of what we can do. And the idea of understanding this is to go and to produce the first movie of Sagittarius star. More problems. How do we mean that? Yeah, fine. More problems. We want to observe the galactic center, Sagittarius star. But Sagittarius star is strongly affected by scattering. Scattering effects in lambda square with respect to the frequency. So the higher frequency, the less scattering. But the higher frequency, the less interesting thing we may have. For example, pulsars. Pulsars at 230 gigahertz, we cannot find. We don't expect to find any pulsars there. The Sagittarius star with the GBA. What we see now is just a Gaussian, because the scattering is breaking all the structure, intrinsic structure of the ring. So how can we use our multi-objective optimization to mitigate this problem? And this is a paper that I submitted very recently. And we were doing these 2 cases. Okay, let's suppose we have this UV coverage, very sparse, 230 gigahertz, and this is our model, and GMVA plus ALMA 2025, next year, with bad weather conditions and some corruptions. Let's see. This is our image, blur image. It will, for example, we will see in Sagittarius star at 230 gigahertz, corrupted with this scattering screen. Our algorithm is able to recover the unscattered ring and the screen that was affecting the faces. Of course, at 230 gigahertz, the scattering is not very strong. So it's not very constrained, because that is one of the reasons why we observe Sagittarius star at 230, because we can, thanks to the scattering is not very strong, we can recover the whole. But in contrast, the screen is harder to recover. However, what if I go to 86 gigahertz and I observe Sagittarius star, and I corrupt it with the expected scattering kernel at 86 gigahertz? Well, do I recover this much more stronger screen, but more similar to the simulated one, and a ring?
not only a ring, but the ring with the expected size at 86 gigahertz, because the ring at 86 gigahertz, because of the spectrum, is expected to be 1.6 microsecond bigger than the one seen by the Studi. Of course, this part is much much thicker, so because the frequency is lower. So we obtained the ring with 1.6 microseconds bigger than the one also at 230 gigahertz. So we match the expectations, the theoretical expectations. But what if another problem of the scattering screen is, what if the scattering screen is moving at 50 or 250 kilometers per second? We don't know. Right now, the scattering screen is not well constrained. Speed of the screen is not well constrained. So how this can affect our data and our reconstruction? And we are able to recover the source, the intrinsic structure, and the evolution of the screen at 50 and 250 kilometers per second. And what are these plots? This is what we call cylindric plots. And is how the pixel I evolves during the 100 minutes that the observation is done. So we see some evolution. It means that this pixel is changing on brightness while the time is passing. This is the evolution of the screen, simulated screen, and this is the evolution we recover with our algorithm. So we can recover the intrinsic structure, no matter what is the velocity is 50 or 250, which is good because we don't know what is the true speed. And how the multi-objective, how this solution can help us to solve this problem. So look, if we try to solve this problem using normal approaches, none of the solutions present the ring structure. Actually, this is what we expect, and this is the solution we get. And this is the solution, for example, Sarah Isaun, 2019 and 2021 was saying, we are not able to see the ring in the intrinsic star, we only see a Gaussian. Sure, it's here. And none of this is a ring. But what if we take this one, for example, this Gaussian, and we self-calibrate, and we explore all the possible solutions? Well, there are a lot of rubbish, and suddenly one ring appears. Nice. So what if we take this, we self-calibrate, and we explore all the solutions again? We start to recover the ring. So because of not exploring all the possible solutions in a traditional way, we were not able to see the ring. But if you explore all the solutions that exist and fit the data, and are recovered thanks to the multi-objective optimization, you end up in the ring. So it's not that we are not able to see the ring of the intrinsic star. It's just we miss a lot of information, a lot of solutions with the traditional method. Of course, this is done in synthetic data, and the work in progress is real.
But this seems to me, sorry, like you're focusing in one local minimum and you're exploring this further, right? If you focus in another one that is not the ring, right? Then you will also produce all these other solutions, right?
Yeah.
So why do you prefer that instead of the other? Because of the theoretical bias.
So this is a very good question, and I tried with all the possible solutions, and more sooner or later you arrive. The one selected here is unblinded. It is blind, sorry, with a pipeline. So what we do is we define some metrics based on the most probable solution and the one with the less chi-square. And this is selected for doing the next step. Is this the only selection? No. Is this the best selection? Probably. Is this one selection that can be justified without many variants? Well, yes. If you start with another, you end up there? Yes. I think I start with this, and after, I don't know, 20 or 25, I also recover ring, but 25 it means a lot of days running as a calibration and running as a calibration. But the probabilities increase very, very, very high.
So you're saying if you keep doing it, but for the other initial conditions, so to speak, you still recover a ring in the end.
In the case that I've done, yes.
Okay.
in synthetic data.
Yeah, that's reassuring. Okay.
Just a second.
Yes,
If we did not know the image that we were to find, because it seems to me that out of the million images, we select that one that looks like the one that we expected.
normally, so we don't know the image that we are going to recover. Because we don't know it.
What I'm saying is that we feel that we have seen the image of M87 because it fits our intuition. This is what we expected, this is what we saw, but this is one solution.
One solution.
And it's not the best solution, it's equivalent solution.
It's one of the possible solutions that fit the data, yes. And there are many solutions that can fit the data and they are not in this, with this shape. What is the true solution? So the steep, we explored many solutions and we gave the probabilities of getting those solutions. The same for M87, but I put here Sagittarius A star because it was the recently major ship. So among of these 12 million images, we also said there are solutions that are not expected what we want to see, that we would like to see the ring, but they are very low probable to appear. But they fit the data. This mathematically fit the data. This mathematically is a solution of the Einstein equation, blah blah blah. Then no, probably not. But it appears and we claim it. And is there?
So this is a frequentist approach.
Sorry, yeah. And then this image that we did here was just the weighted average of all the images here.
So our expectation give us a probability distribution, let's say, right? And what we see as the final image is the solution with the highest probability.
Yes,
That's what I understand.
that's what exactly the Bayesian methods are doing. They are exploring all the possibilities with all the tons of a priori, and then the output is the posterior.
But
The most probable posterior.
but the EHT did not do the ring.
Yes,
They did.
they did. We use for DHT one RML,
Yes.
two RML, sorry, one Bayesian, and clean, and all of them converge to the same.
And that's the probability distribution that you saw in.
Yes.
Okay, they are the combined effect.
They combine. These 12 millions are 12 millions taking into account, I think there was 8 million from here, 1 million from here, and the rest from Bayesian exploration.
How much was the Bayesian in percent?
I don't remember, but it was, I don't remember. I can.
But it's a small percentage of the total, right?
No, Bayesian was actually the second. I think it was bigger than Cliff.
Oh,
Yeah, because there were more people working on Bayesian than people working on
okay.
Cliff. And there have been more studies, independent studies of M87, for example, with result, which is another Bayesian approach that give also the ring with response rate, that give also the ring, and the only one which is not giving consistently the ring in non-M87 or Sagittarius star is the one using clean, because it's the one you can cheat the most.
Okay, that makes sense.
So yeah, but I just only were the conclusions where I wanted to show, but I think just I'm happy to take questions and to discuss rather than read the conclusions. Thank you.
Only because I wanted to see how the image changes with time. I
Yeah.
observe M87 now, and I observe it a month later, or a year later, and so on. How do I know that I have selected the same solution so that I see the evolution and not because the various images are different?
Yeah. So I didn't talk about dynamic imaging, but there are different approaches. The one you're saying will come from the snapshot imaging. So we have one epoch we do imaging, and we create a movie with this snapshot, which have this problem. Do they have the same solution? No. They can't. They may not have it. The good solution will be to combine all the data, to combine all the days, and do a movie with all the days together, with all the combined. Or what I was doing for my paper in dynamics, it was to explore all the solutions with a multi-objective and use the same solution in the sense of the most probable solution or the more repeated solution for every frame to construct the movie. But with a consistent approach, not just clean this one, and make a movie. This can be quite different. Yes.
But the first approach doesn't increase the data volume
Yes.
by a lot.
By a lot.
If for one snapshot you have 12 million, you
Well-
do that for many snapshots.
Well, those algorithms are thought for DHT and NGHT, the latest development. So we are talking about 1,000 visibilities. If you combine 2,000, 3,000, not that many. Million is another topic.
I was wondering if there is the computational power for that.
The computational power for our algorithms in the paper, we give it. For the rest of algorithms, I'm not sure. So I can tell you, for example, resolve is quite expensive. It is yesterday when told they were saying it, and it takes for the image, the good image of feminism with the jet and everything, they were having 1 million pixels and 2 million of parameters to explore. So they were solving 2 million times 1 million problems, and for every problem they solve an optimization, times iterations. Snapshot. There is a movie of MD7 with Resolve, and it's published in Nature, and maybe there is the computational power that they took for the movie. For 2000, combined 2017 and 2018 observation. But I don't remember right now the numbers. But you can do it with your computer. Yes?
One question. If you have a better UV coverage, do you think that the problem clean? I'm thinking in ALMA, what you have better UV coverage than VLBI, but and everyone uses clean.
Yeah. In ALMA, the degrees of freedom is, for saying in some way, is much less because you have much better UV coverage. So you have to do it very bad to cheat doing clean.
Okay.
In ALMA, I tried to just run a standard RML, and it was a little bit slower than clean because clean was good enough. With so many visibilities. But still, you have to know, because when I give these workshops for students, I take ALMA and I do self-calibration to a smiley face, and even with ALMA, you can end up in a smiley face. Or in a pirate, or in Valencia, flag, or whatever you want. You have to take care of what you are doing, but it's much harder to write.
Yeah.
Yeah.
I asked how many.
No,
So, it might be counterintuitive, but I would expect when you have dynamical evolution, if you're trying to reconstruct a movie, it should be easier than a snapshot because you have too many priors, right? I mean, the different snapshots have to be connected. And that, to me, means that you would have less freedom, less degrees of freedom. Is that true, or am I completely off?
so this is dependent on the approach you want to use. For example, the approach that I did for the dynamic imaging algorithm that I developed, it was defining the temporal entropy. So you impose a regularizer, you want to minimize, or you want to maximize the temporal entropy. So ask to your movie to be the most consistent possible. And this increases your degree of freedom because you have the solutions, the per frame time the number of frames. You have more degree of freedom.
But if you combine everything and you do some machine learning interpolation, then you are restricted to your point of view. It depends on how you want to deal with the problem. Every snapshot or as a whole, you may have one way, one philosophy or another one.
Yeah.
Published dynamic imaging algorithm published till this moment, there are 4 or 5, there are not so many. It's a hot topic. So there is some machine learning in process that I don't understand because it's not published yet, so I haven't read the details, but it seems to perform very well. But I don't know the philosophy behind this.
And I also have a question. So in this multi-objective optimization, so I understand that you can give some weights to your regularizer.
No, the weights,
You cannot.
the weights are a byproduct of the problem.
They are
You
the-
cannot find them.
Exactly. So, well, okay. So at the end, you will get exactly. So
Yes.
but can you use actually this then to plug in back?
Yes. So what we do is we solve our multi-objective, we have weights, and we say to people using standard RML, those are the weights you have to use. Because we already explored all of them. And those are the best ones. So they are restricting the search to our.
So from a Bayesian point of view, like giving the value. We don't do-
Yes, but we don't have to see optimization as a Bayesian, but it's like giving the priors.
Okay, one last question. Yeah.
Yes. So in, for example, each imaging as a traditional RML method, it's also possible to do self-calibration.
Yeah.
To adjust some telescope gains. Is it also possible with the multi-objective? Does it also solve for gains in some way or?
We are thinking about it. Right now, the self-calibration is not, we have to do it. You have the final image, you do self-calibration, you apply again. We are doing some computations to include the gains in the computation, but it's a little bit far now. But we have it in our mind. I think it's the correct way to go. Mostly for dynamic imaging, where you have only every 4 seconds, you have one frame with very sparse UV coverage, 7 antenna, 4 seconds is not.
Okay, so we stop here and thanks, Alejandro.